So welcome to the final session of today. Our speaker is Zhengzhong Jin, now at MIT, speaking on indistinguishability obfuscation via mathematical proofs of equivalence.
Thanks for the introduction. So this talk is about indistinguishability obfuscation, where mathematical proof of equivalence. And I'm Zhengzhong Jin. This work is joined with Abhishek Jain. So what is program obfuscation? So the indistinguishability obfuscation is an algorithm that takes the source code of some program as input and output an obfuscated program that looks unintelligible. And we also want the obfuscated program to preserve the functionality of the input program. So that means for every input to the obfuscated program, it should produce the same output as the original program. And the security of I/O is defined as the following indistinguishability security. So it can be viewed as a game between an adversary and a challenger. So this challenger will try to decide whether this adversary's attack for I/O is successful or not. So initially, the adversary chooses two circuits or two programs, C0 and C1, and send them to this challenger. And the challenger will randomly flip a coin B and obfuscate one of the two programs and send the obfuscated program back to this adversary. And the adversary is required to guess which program is obfuscated. So the adversary sends back the guessing bit B prime to this challenger. In the end, the challenger will verify whether the two programs C0 and C1 are functionality equivalent. So functionality equivalence means that for every input X, C0 of X will has the same output as C1 of X. So the challenger also checks whether B prime equals B. And if both checking passes, then this challenger declares this adversary wins the game. So the security of I/O requires that the probability for any adversary wins the game is bounded by half plus some negligible function. So intuitively, so if the adversary randomly guesses this bit B prime, then it will win this game with probability no more than half. So intuitively, this indistinguishability security requires that for any adversary, its ability to distinguish the obfuscated programs of C0 and C1 cannot be much better than a random guessing. And here, I want to emphasize this in this security definition, it's important to check the functionality equivalence of C0 and C1. Because if C0 and C1 differs at some input point X0, then the adversary can certainly distinguish the obfuscated programs of C0 and C1 by running the obfuscated program at this point X0 and observe its output. So previously, I/O is a very important topic. It is sometimes called cryptographic complete problem, because if you know how to build I/O, then you can use it to achieve many other cryptographic tasks. So they include advanced encryption schemes or some succinct cryptographic proof systems. It also has applications in complexity theory, such as the hardness of Nash equilibrium. So I/O is very useful. So can we build them? So this question has been studied for quite a long time. And recently, by the breakthrough work by Jianling and Sahai, they show how to build I/O for general circuits from well-founded assumptions. So in this work, we studied the following question. Can we build I/O for Turing machines? So why we care about the Turing machines? Why isn't a circuit model good enough? So the first reason is that Turing machine is a natural representation for computer programs. For example, when we are writing program in some high-level programming language, the source code we wrote indeed can be viewed as a Turing machine because we are not specifying how the gates and the wires are connected in a circuit. And the second and the most important reason is that Turing machine can support for any unbounded input length. And this is very different from the circuit model because a circuit can only support for a fixed length input. So this leads also to the third point. So if we consider the notion of I/O for Turing machines, then both of the input program and the obfuscated program are both represented as a Turing machine. And ideally, the obfuscated Turing machine size should only depend polynomially on the size of the input Turing machine. So its size could be much smaller than the obfuscated program in the circuit model. So previously, there is also a long line of work constructing I/O for Turing machines, but all of those works can only support obfuscation for bounded input programs. And the reason is as follows. To build I/O for Turing machines, they need to prove the security of I/O. So to prove the security, we usually first assume there exists some adversary for I/O, and we use this adversary for I/O to build some reduction algorithm that can break the underlying assumption. However, in the previous works constructing I/O for Turing machines, the reduction algorithm runs in the 2 to the input length time. So here, the input length is the input length of the circuit being obfuscated. So to prove the security, they need to further assume the sub-exponential hardness of the underlying assumption. So they assume the underlying assumption is 2 to the lambda to the c hard. So here, c is a constant between 0 and 1. And they set the security parameter. So the security parameter lambda is the size of the underlying assumption. They set this security parameter large enough such that this 2 to the lambda to the c can be larger than the running time of this reduction algorithm. In this way, they prove the security. The issue is that this also set an upper bound for the input length because the input length cannot be larger than the security parameter. So why there is a 2 to the input length loss in their security reduction? So is such a 2 to the input length loss in the security reduction inherent, or is it just a technical issue? So in fact, there is a meta reduction argument showing that this 2 to the input length loss is kind of inherent. So the observation is that to prove the security of I/O, if the adversary always chooses 2 circuits that are functionality equivalent, then the reduction algorithm should break the underlying assumption. And on the other hand, if we switch this adversary to a fake adversary that always chooses 2 circuits that differs at some point x star, then such an adversary always exists in polynomial time, because if this adversary knows this point x star, then he can certainly distinguish the obfuscated program by running the obfuscated program at this point x star and observe its output. So in this case, the reduction algorithm shouldn't work. Now, from this argument, it seems to suggest that this reduction algorithm must know whether the functionality equivalence of C0 and C1 holds. So intuitively, that's why this reduction algorithm needs to run in the 2 to the input length time. And in fact, such a 2 to the input length loss sources from the following non-falsifiability aspect of the security definition of I/O. So let's recall the I/O definition. So we view this definition as a game between an adversary and a challenger. And the challenger needs to check the functionality equivalence to decide whether the adversary's attack is successful or not. But this checking is inefficient because the challenger needs to enumerate all possible inputs to C0 and C1 and check if they output the same output. So we call this kind of security definition non-falsifiable because the running time of the challenger is not polynomial. And this is the source of the issue. So in fact, such a non-falsifiable definition appears in many other places in cryptography. For example, it also appears in the succinct proof systems. And sometimes you can formalize this intuition to obtain a formal impossibility result. So in this talk, the question of how to build I/O for Turing machines essentially boils down to the following question. So how can we overcome this non-falsifiability barrier? And previously, there's also another line of work try to overcome this 2 to the input length barrier in the I/O reduction, in the I/O security reduction. But all of those works requires the functionality equivalence of the 2 circuits to be decidable by some polynomial time algorithm. So in this work, we are going to depart from the previous route. So our starting point is the following key observation. We observe that if we want to use I/O to build some other applications, then it seems that we always write down a mathematical proof of functionality equivalence for the circuits that we are interested in. The reason is as follows. So suppose we want to use I/O to build some other applications. then in the security, we need to prove the security proof. We need to prove the security of that application. And how are we going to use the I/O security to prove the security of that application? So usually, we think hard to build two programs, C0 and C1, and we write down a mathematical proof of functionality equivalence for these two programs, C0 and C1. Only then we can apply the security of I/O to derive that the obfuscated programs of C0 and C1 are also indistinguishable. And from this process, it seems that we always write down such a mathematical proof of functionality equivalence for these two circuits, C0 and C1, that we are interested in. And furthermore, I can further assume such a proof has a very short length. In particular, its length must be much shorter than the 2 to the input length, because otherwise our brain cannot even have enough time to even process it. So in this work, we crucially relies on this short mathematical proof of functionality equivalence to bypass this 2 to the input length rules in the I/O security reduction. So what we are going to do is to leverage this short mathematical proof to build an efficient reduction algorithm in the security proof of I/O. So by using this approach, we obtain the following result. Our work built the I/O for any two Turing machines, M1 and M2, if the functionality equivalence of these two Turing machines can be proven in Cook theory PV. And our construction is based on the well-founded cryptographic assumptions. So what is Cook theory PV? So PV is a formal logic system that formalizes the intuition of polynomial time reasoning. And it doesn't allow a general induction rule, but it allows the following polynomial time induction rule. So intuitively, it says that if you can prove that some proposition phi it holds for n equals 0, and if you can prove that for any integer n, this phi n implies phi 2n and phi 2n plus 1, then you can conclude that this phi n holds for any integer n. And the Cook theory PV also allows the introduction of new function symbols. So you can introduce any polynomial time function symbols in theory PV. So the common arithmetical operations, including addition, subtraction, and these arithmetical operations can all be introduced in this way. And also you can introduce basic logic symbols. So what theorems can theory PV prove? So previously, it's known that most of the polynomial time algorithms has a correctness proof in theory PV. And most of the basic linear algebra theorems, including basic properties about matrix and the basic properties about the determinants, can be formalized in theory PV. And also, many of the combinatorial theorems, including Cook-Levin theorem and some form of the PCP theorem, has proof in theory PV. In this work, we further show that many cryptographic algorithms fall in this natural algorithm category. And we show that the correctness of L-gamma encryption and the recursive encryption and the punctual PRFs can be formalized in theory PV. So punctual PRF is a building block in many I/O-based cryptographic applications. And we hope those examples can be served as guidelines for you to build your own applications using our result. So is there any theorems that cannot be provable in theory PV? Indeed, assuming the factoring problem is hard. So the following theorems are unlikely to be proven in theory PV. The first theorem is the Fermat-Little theorem, and the second theorem is the correctness for any algorithms that decide primes in polynomial time. So both of them follows from the witnessing theorem. So in this work, how do we leverage this mathematical proof of functionality equivalence in the security reduction of I/O? Next, I'm going to show you a very high-level overview of our techniques. So before I show you our approach, let's first think about what information does a mathematical proof provide. So that means what's so special about a mathematical proof that can distinguish it from, let's say, a random string. So one feature of mathematical proof is that it has some additional structures. So the most important structure is that it has the following localness property. So the localness property says that each line of the mathematical proof only depends on constant number of previous lines. And in some logic systems, such as propositional logic system, each line of the proof is also a circuit because each line is a Boolean formula, so it can be viewed as a circuit. So in this talk, I will use the propositional logic we use is the extended frag system. And in the rest of this talk, I will mainly focus on the extended frag system as the proof of equivalence logic system. Since every proof in theory PV can be translated to a polynomial size extended frag system proof. So next, I will show you how to bypass the 2 to the input length barrier using the extended frag proofs. The high-level idea is as follows. So to prove the security of I/O, we are going to use a hybrid argument. So at the two ends of this hybrid argument are the obfuscated programs of C0 and obfuscated programs of C1. And we are going to build a series of intermediate hybrid. And each hybrid is an obfuscation of a circuit. And if you look at any two adjacent circuit, they are almost the same, except for very small portion of differences. So here, the differences is marked in this green block and the red block. And we can argue the functionality equivalence of any two adjacent circuits in a local way. So that means there is a polynomial time algorithm that can decide whether the two adjacent circuits are functionality equivalent or not in polynomial time. And this is crucial because it makes the I/O definition falsifiable. So in this work, we built I/O for locally equivalent circuits with a loose independent of the input length. So here, the local equivalent circuit, for the definition of local equivalent circuit, I will show you later. So in this hybrid argument, for each two adjacent hybrid, the security loss is independent of the input length. So how do we build this series of hybrid? In this work, we show that if you have a polynomial size extended frag proof of functionality equivalence between C0 and C1, then you can translate this proof to a series of intermediate circuits where each two adjacent circuits are locally equivalent. And if you have a polynomial size this extended frag proof, then the number of hybrids is also a polynomial. So the total loss of this hybrid argument is a polynomial times loss that is independent of the input length. In this way, we bypass the 2 to the input length barrier. So is there any questions?
Yeah. So you need to prove for all x, C0 x equals C1. Oh, that's equivalence. That's what the three thing.
Yes.
3 lines. Okay.
Yes. So the locally equivalence, in the locally equivalence, we only care about the difference of two adjacent circuits, and the difference of two adjacent circuits is very small. So that's why we can decide the functionality equivalence for two adjacent circuits in polynomial time.
Yeah. So, I mean, maybe you're going to say something about this, but obviously you got an extended Frege proof that C0 and C1 are equivalent. It's not obvious that you've got sort of, the things you're talking about are not necessarily C0 or C1. They don't look. They can be completely different circuits.
Yes, good question. So in fact, there is some padding going on. So we in fact pad the C0 and C1 to some larger circuit, and we use the And in this padding, there are some dummy circuits. So we made changes to those dummy circuits in this series of hybrid.
So you're keeping track basically of all of the circuits that show up in this EM proof as you're going along. That makes sense.
Any questions?
But just to clarify, so the way you make use of the EF proof is that there's a sequence of intermediate circuits where it starts from C0 and to C1, and each two adjacent circuits are locally equivalent.
Yes. So,
sorry, can you say anything about each step? Does each step correspond to one line in the proof, or is it a more complicated correspondence?
good question. So each line, in fact, corresponds to one line in proof. I will show you later. Okay. So in the rest of this talk, I'm going to show you more technical details. First, I will show you how to use the extended track proof to translate it to a series of local changes, a series of locally equivalent circuits. And next, I will show you how to use I/O for locally equivalent circuits without a loss that is due to the equivalence use. And finally, I will show you how to extend this idea to use I/O for unbounded input length to machines. So let's first focus on how to translate this EF proof to locally equivalent circuits. So let me first define what is local equivalence. So we say two circuits C and C prime are locally equivalent if they are almost the same with the same topology, except for a very small size subcircuit of size log n. And we require these two subcircuits are functionality equivalent. So that means for every gate outside of these two subcircuits, they are exactly the same. So in this picture, the subcircuit is marked in the green block and the red block. And we allow the gates within the subcircuit to be different, but we require these two subcircuits compute the same function. So the subcircuits are functionality equivalent. So here, the subcircuit is defined as induce the subgraph of the entire circuit, because the circuit, we can view the circuit as a directed acyclic graph. So the subcircuit is just induce the subgraph given a subset of gates. And these two subcircuits has the same position in the C and C prime. Any question?
The identification of the subject is given.
Yes. Yeah. Yeah. The position of this subgraph is given. So, and in this part of the technical section, we are going to show that if you have an extended track proof, then you can translate it to a series of locally equivalent circuits. So, and the first circuit in this series of circuits is C0, and the last circuit of this series of circuits is C1. And any two adjacent circuits are locally equivalent. And so next, I'm going to take an alternative view of this series of circuits. So I'm going to view this series of circuits as a series of local changes, because if you view any two adjacent circuits, they are locally equivalent. But so it can be viewed as the transition from one circuit to its next circuit can be viewed as taking a small subcircuit from the entire circuit and replace it with some functionality equivalent subcircuit. And we apply this series of local changes one by one to the circuit C0. So in the end, we arrive at a circuit C1. So in the rest of this talk, I'm going to show you this translation from the extended track proof to this series of local change. But for simplicity of this talk, I'm going to ignore the topology change for this series of local changes. So I'm allowed to add a gate or delete gate freely. So this issue can be solved by padding the circuit to a larger circuit, and we can simulate the topological change by changing the functionality of the gates. And for simplicity, I will also use multi-array gates. So multi-array gates can be always simulated by the gates of constant arity. So next, I'm going to describe this series of local changes.
Yep. What's the arity of the multi-array gate? Is it log?
It's poly. So but you can, yeah, it's a poly AND gate. You will see that. So next, I'm going to describe this series of local changes. So this series of local changes consists of multiple stages, and in each stage there are multiple steps. So in the first stage, I'm going to grow this circuit C1 besides this circuit C0, and each time I'm going to add one gate in C1. So essentially, in this stage, we'll add gates in C1 one by one to this circuit, and the input to this circuit C1 is still set to be X. And at any time, the output of this entire circuit is still set to be the output of the circuit C0. And now you can argue the functionality equivalence for any two junction steps in this stage. So at any step, I add a gate, but the output of that gate is never used anywhere. So it preserves the functionality equivalence. So let's denote the output of C0 as O0 and output of C1 as O1. So at this point, the output of the entire circuit is set to be O0. So in the next stage, I'm going to grow the extended Frege proof slowly inside of the circuit. So suppose we have an extended Frege proof of functionality equivalence between C0 and C1. And let's denote the proof as θ1 to θl. So each θi is a line in the proof. So at the beginning of this stage, the circuit looks like this. So we have both C0 and C1, and the output is set to be O0. And in this stage, I'm going to add, in each step of this stage, I'm going to add one line of the proof to the output of the entire circuit. So at the ith step, the output of the entire circuit is set to be O0 and a series of theta from θ1 to θi. And the intuition behind this stage is that each θi is also true because it's aligned in the proof. So for any input, this θi will be evaluated to 1. Then the output of the entire circuit will compute O0 and a series of 1s, which is still O0. So it preserves the functionality of the circuit. And next, I'm going to show you at each step of this stage, it also preserves the functionality equivalence can be argued locally. The reason is that for the ith step of this in this stage, so before we add θi, the circuit computes C0 and a series of theta from θ1 to θi minus 1. And after we add θi, the circuit computes C0 of X and θ1 to θi minus 1, and there is an additional θi in the end. So the functionality equivalence can be argued as follows. So suppose the ith line θi is derived by model exponents. So that means there exists some proposition P, and proposition P implies Q somewhere in the proof. And the current θi is a proposition Q. Then we can identify the position of this P, and P implies Q and Q. So in this series of and if we look at the subcircuit formed by this P implies Q and Q. So before we add θi, it computes a function on the left-hand side, which is this P and P implies Q. And after we add θi, it computes a function on the right-hand side. And you can see the functionality equivalence for the circuit before we add θi and the functionality and the circuit after we add θi can be argued by only look at this subcircuit. So we can argue the functionality equivalence locally. So in the next stage, once I have added all of the proofs in the output of the circuit, I can switch the output from O0 to O1. And the intuition behind this stage is that if we look at the last line, θl, it must be a proposition saying the output of O0 is the same as the output of O1. C1. So if you look at the subcircuit formed by O0 and theta L, then before this switching, it computes a function on the left-hand side. And after we do this switching, it computes a function on the right-hand side. So the functionality equivalence of this switching step can also be argued in a local way. And the next, once I switch the output of the entire circuit to use O1, I can shrink this proof. So I can delete each line of the proof one by one in the reverse order that I add them. So in the end of at the end of this stage, I can delete all of the proofs and obtain a circuit that have both C0 and C1 hardwired. And the output of the entire circuit is now set to be C1, set to be O1. So the functionality equivalence can also be argued in a local way, similar to the growing the proof stage. Finally, finally, the circuit look like this. So we have both C0 and C1, and the output of the circuit is set to be O1. But at the beginning of this stage, the output of C0 is never used anywhere. So we can delete them in the reverse topological order. So at the end of this stage, we arrive at this circuit C1. So this now I've shown you how to translate from C0 to C1 using a series of local changes. And the functionality equivalence at this stage can also be argued in a similar way as before. Any questions?
Yeah, can you go back to the previous? Can you say just a little bit more about postal equivalence here? Because I understood when you got rid of O0, that was good. And I think I see how you would get induction on like theta L minus 1 because the children in C1 also need to behave correctly. Can you say a little about that?
Sorry.
Can you say a little about how you get rid of theta L minus 1?
Because theta L minus 1 is only so all of the proofs theta I, it only depends on some lines, some other lines in the proof. So yeah, so it's the reverse. So essentially we are reversing the procedure that we add those proofs. So the only difference is that the first proposition now becomes O1 instead of O0, but it doesn't affect this procedure. Because when you add a theta I, it only depends on other theta, but not O0.
The first part, everything is if and only if. Everything's actually logical equivalent, so you can just be symmetric.
Oh, okay.
So next, I'm going to show you how to build I/O for locally equivalent circuits without a rules that is exponential in the input length. Yep.
It seems like those steps have a constant locality.
Right. Yep.
So you don't even need the log n.
The logarithm comes from the fact that there is some additional padding, because in this procedure I change the topology of the circuit, but in the reality I cannot change the topology because of this I/O construction. So I use some padding will introduce a logarithm factor.
Because the lines of the proof actually be pretty long too.
Good question. So if we use extended frame, then we can always shorten the size of each line. So our initial idea is to build this obfuscation using a gate-by-gate obfuscation template, using a new gate-by-gate obfuscation template. And the idea is that we're going to take each gate in the input circuit G, and let its input wires denoted by L and R, and its output wire denoted by O. And to obfuscate this gate, we are going to use I/O for circuit to obfuscate a circuit CG. So this CG will emulate the functionality of this gate G. And to achieve this, we are going to use some encryption algorithm and authentication mechanism to sign the wire values and encrypt them. So the circuit CG will take the ciphertext of its two input wires as input, and it will internally decrypt those ciphertext and do the computation for this gate G and output an encryption of the output wire. So the key feature, so the main advantage of this gate-by-gate obfuscation template is that it can preserve the topology of the input circuit. So, and this feature is important for us to overcome this due to the input length barrier in the security reduction. So let's consider two circuits C and C prime that are locally equivalent, and we want to prove this gate-by-gate obfuscation template. This gate-by-gate obfuscation of them are also indistinguishable without a loss that is exponential in the input length. So how do we argue this? So we first leverage this topological preserving property. So we can identify what is the position of the obfuscated subcircuit in the obfuscated program. And note that each gate outside of these two subcircuits are exactly the same in C and C prime. So the gate-by-gate obfuscation of them are also identically distributed. So we can simply ignore them and only focus on the obfuscation of these two subcircuits. And to argue the obfuscation of these two subcircuits are indistinguishable, we can use a reduction that has loss due to the input length loss due to the input length to this subcircuit. And since the size of this subcircuit is very small, we can bypass the due to the input length barrier. Any questions?
That's where the order logging comes in, like the fact that like these obfuscations blow up the.
Good question. So, so because of the size of the subcircuit is the order of log n. So in this step, the security loss is at least 2 to the log n, which is a polynomial. Any further question? Oh, good, right. Yes. So in fact the input size of CG may depend on the security parameter, but it's independent of the input length because the input length could be much larger than the security parameter. So, but this idea doesn't work directly because of the following mix and match attack. So, so consider the following adversary that can observe the obfuscated program. So the adversary can run this obfuscated program for two different input X and X prime, and it can record the intermediate ciphertext of these two executions. And now the adversary can mix the left ciphertext for one of the execution and mix it with the ciphertext of the other execution and feed them to the obfuscated gate. So now the obfuscated gate will reveal more information than it should do, because normally if we run this program honestly, then so for some combination of the input combinations, this obfuscated gate will never be executed. So intuitively, this adversary can force this obfuscated gate to reveal more information than it should do. So we cannot prove its security. So our next idea is that we are going to modify this circuit CG to have it take the entire input to the input circuit as the input. And it will internally check the consistency between, about its ciphertext with respect to the input. The issue with this approach is that the size of the input length is too long, because we are only allowed to use I/O for small size circuit. So to fix this, our idea is to replace this input with the wires that this gate G depends on. Because in some setting, this gate G may not depend on the entire input. For example, if the depth of this circuit is very shallow, then the gate G may only depend on constant number of inputs. So let me define this gate dependence. So for any wire in the circuit, I'm going to define this depth W. So depth W consists of all the wires that W depends on. And I'm going to define a capital W. So it consists of all the ciphertext in the depth W. And here, the capital CTW consists of, is defined as an index set. So every ciphertext in it is indexed by the wires. And now I can replace this input with the capital CTL and capital CTR in the construction of this circuit CG. So circuit CG will take the capital CTL and capital CTR as input, and it will internally check the consistency. So it will internally check this capital CTL and capital CTR contains the same ciphertext in the intersection of depth L and depth R. But this also doesn't work directly because for a general circuit, this capital CTL and capital CTR may also contain the entire input. So our next idea is to hash capital CTL and capital CTR using a hash function. And this hash is done outside of the construction of this circuit CG. So we hash this capital CTR to some small hash value and replace capital CTL and capital CTR with their hash values in the construction of this circuit CG. But we have another issue because previously, since we know the full information of capital CTL and capital CTR, we can check the consistency. But now we only have access to their hash values. So it's not clear how to check the consistency. So our third idea is to apply a SNARG. So SNARG is a very short cryptographic proof. So this SNARG will generate a proof pi. This proof will prove that there exists a pre-image of this hash function to this HL and HR, such that the pre-images are consistent. And such a SNARG is only secure against polynomial time adversary. So now I can modify the construction of CG as follows. So we'll have this CG further take this proof pi as input, and it will internally check the consistency. So it will internally verify this proof pi. And it will do the other things as before, such as this decryption, compute this gate G, and re-encrypt the output wire. But this also doesn't work directly because to use the SNARGs inside of I/O, we need this statistical security of SNARGs because I/O security requires the functionality equivalence, and the functionality equivalence is a statistical requirement. So our final idea is to use I/O-friendly SNARG. And the key observation here is that we, in fact, only care about the consistency of capital CTL and the capital CTR with their intersection, with the subcircuit. Because at any time in the hybrid argument, we only change the gates in this subcircuit. So we will use some SNARG with additional soundness property called somewhere statistical soundness, which says that if capital CTL and capital CTR are not consistent in the subcircuit, then even unbounded time cheating adversary cannot find some accepting proof. And in our work, we construct such a SNARG from the recent work by CGG21. So finally, here is a summary of our construction of this I/O for locally equivalent circuits. So for any gate in the input circuit, we are going to use I/O for circuit to obfuscate a circuit CG, which emulates the functionality of this gate G. And outside of this circuit CG, we are going to hash capital CTL and capital CTR and generate a proof pi. This proof pi will prove the consistency for these two hash values. And this circuit CG will take these hash values and this consistency proof to ensure the consistency. So this concludes the I/O construction. So finally, let me show you how to extend this idea to build I/O for Turing machines. So our starting point is the propositional translation. So in Cook's original work, he shows that if you have a proof in Cook theory PV, then you can translate it to a polynomial size extended flag proof. And in our case, the PV proof is the functionality equivalence between two Turing machines, M1 and M2. And given any fixed length n, fixed input length n, we can obtain a polynomial size extended flag proof of functionality equivalence between C1n and C2n. So here, C1n and C2n are the circuits that emulate the computation of this Turing machine, M1 and M2. So our next natural idea is to apply this I/O for locally equivalent circuits to this circuit C1 and C2. Because I/O for locally equivalent circuits allow us to bypass the 2 to the input length loss in the security reduction once you have extended flag proof. So to build I/O for Turing machine, here is our initial attempt. So given any Turing machine, we're going to first set a super polynomial upper bound, a slightly super polynomial upper bound, N0 on its input length. So N0 is set to be lambda to the log lambda. And for any input length n that is bounded by this N0, we are going to convert this Turing machine to a circuit that emulates the computation of this Turing machine for the input length n. So we can obtain a series of circuits from C1 to C capital N0. And then we apply this I/O for locally equivalent circuits to obtain the obfuscated programs for each of those circuits. And we put these obfuscated programs together as the obfuscated Turing machine. So this is the initial idea, but this doesn't work directly because if we look at the obfuscator running time, it will be at least N0, which is a super polynomial. So to make this obfuscation efficient, we are going to leverage the uniform description of these circuits from C1 to Cn0. And the idea is that since all of those circuits is generated by this Turing machine, so there exists a very small size circuit that it will take the input length n and the index I, and it will output the description of the IOS gate in the circuit Cn. So now we can use this small size description circuit to generate the obfuscation of Cn. So let's first recall how do we obfuscate the n circuit Cn. So what we are going to do is, so what we did is we're going to take each gate in the circuit Cn and use I/O to obfuscate a gate, obfuscate a circuit Cgn from Cg1 to Cg2, etc. And our idea is to leverage this uniform description circuit to generate the I/O obfuscation of this Cgi. So this leads to the following efficient construction of I/O for Turing machine. So given a Turing machine, we first build some uniform version of this circuit Cg. And this uniform version of circuit Cg will take input length n and then index I. So the index I will specify what is it will specify a gate in the circuit Cn. And it also takes the input, also take the same input as the circuit Cg. So this uniform circuit will internally compute the description of the IOS gate of Cn and do everything this Cg need to do. And we just use I/O for circuit to obfuscate this circuit UC to obtain obfuscated program for Turing machines. Any questions? Yeah, so finally, let me summarize the result and discuss some future directions. So in this work, we establish a correspondence between the inference rules of a logic system to prove the functionality equivalence of two programs, and the techniques that allow us to argue the indistinguishability for I/O. And for the logic system, we consider the extended flag was group theory PV, And the corresponding techniques we develop are the I/O for locally equivalent circuits. So the one future direction is to consider how to extend this idea to achieve I/O for Turing machines with functionality equivalence provable in ZFC. And the question is how to deal with the how to develop the corresponding proof techniques to deal with the inference rules in ZFC. And as a week ago, we can also consider other logic systems in bounded arithmetics. Thank you.
Questions? General question, you did local obfuscation. How general is that? You can have two circuits that do the same thing, they're very different from each other. Can that always be a series of local equivalences? On that.
Yeah, I think so for the current techniques, I think the local equivalence can also be proven in extended fact because you can enumerate the possible inputs to this subset. But maybe there is some way to, for example, generalize this gate by gate obfuscation to some Turing machine by Turing machine obfuscation, and then you will have achieve more things.
Questions?